Let's see, let's take a look at a quick couple of examples here of separable differential equations, or exact DEs. So example, this is number 4 in the exercises. We want to check to see if this is an exact equation. 2xy squared plus 2y plus 2x squared y plus 2x y prime equals 0. And if it is exact, we want to go ahead and solve it. So again, we want to think of this as our m, this is our n, so we want to take m sub y minus equal n sub x. That's our question. Okay, so m sub y is equal to 4xy plus 2, and n sub x is equal to 4xy plus 2. Check. Good. Now we want to find f. Right, so we anti-differentiate m with respect to x, and so we would get 2xy squared plus 2y dx. Looks like that's going to be x squared y squared, right, plus 2xy plus an unknown function of y. Okay, now I'm going to use a different technique at this point, just to show you that there is a different technique, and that is that if this is my function f, then f sub y should be equal to n. And so if I take my f sub y using this expression, right, I get, let's see, 2x squared y plus 2x. And the question is, there's my question, is that equal to 2x squared y plus 2x? And it is. Okay, so in this case I don't have, oh, I forgot, let me erase that real quick before you have a chance to see it. I forgot, oh, yes, I want a g prime of y here because I'm differentiating on y. Good. And so is that equal to x squared y plus 2x, the n side here? And it is. And so we can see that we don't need the g of y in this case. And so our solution is x squared y squared plus 2xy equals a constant c. And now you would solve for c if we had an initial condition, right? As usual. Good. In this case we don't. So let's try another one. This is number 2 in the exercises. 2x plus 4y plus 2x minus 2y, y prime, equals 0. Okay, so m sub y is equal to 4, n sub x is equal to 2. Those things are not equal, so not exact. Very good. Alright, so now I wanted to make a point here, and it is possible. So suppose that we have m plus n dy over dx equals 0, and it is currently not exact. So our question now is it possible to find a function mu of xy? Can you guys write your mu's? Mu of xy such that when we multiply our equation through by mu, m, oh gosh, m mu plus, hopefully those look different, n mu dy over dx equals 0 is now exact. Well, what would have to be true? Then we need that the partial derivative of m times mu, my m's and my mu's are starting to look alike, should be equal to n mu x, right? Good. let's continue on with this and see what the restrictions are on mu. And so this would be m sub y times mu, I'm using the product rule, plus m mu sub y, it would be equal to n sub x times mu plus n times mu sub x. Good. Now, what about this differential equation? Okay, this is a partial differential equation. A partial differential equation in mu, and it in fact is harder than the original differential equation. So we made the problem harder, and we don't solve partial differential equations in this class. So therefore, what are we going to do? Well, we're going to try to simplify. Instead of trying to solve this, we will try to assume first that mu is a function of x alone. How does that simplify our equation? So I'm just rewriting our equation straight down here, and so we have our my mu plus mu sub y now is going to be 0, and then we have our n sub x times mu, and then this last expression becomes n times d mu over dx, right? And so if this is the case, if mu is a function of x alone, then we should be able to write, I can bring this over, my minus nx equals n times d mu over dx, right? Oops. And so then we have, sorry about that, things are flying around here, my minus nx divided by n is equal to d mu over dx. Good. So if this is an expression of x alone, we can solve it for mu, right? Because this equation then would be separable, right? You'd have mu times a function of x equals d mu over dx. Okay, so similarly, what happens, let's go back to that start, assume that the mu is a function of y alone. So we're assuming that it was not a function of x. Then what's our equation look like? Let's see, it's going to be hard to write. This was our original up here. Did you write it down somewhere? Here, I'll just write down what the result is. You get m sub y mu plus m d mu over dy is equal to n sub x times mu plus 0. Okay, and now we can solve that for d mu over dy. That's going to be mu times, and this is going to look very similar to what we just had, n sub x minus m sub y divided by m. Alright, so this would be an expression in y alone. Okay, then we could solve for mu. But of course, solving for mu, you're not finished at that point, right? As soon as you solve for mu, then you got to go back and solve the original differential equation. Okay, so this looks really messy right here. Do you have to memorize all this stuff? No. What I want you to do is I want you to remember what the original idea was. And the original idea was, once you have the original differential equation, right, then multiplying by mu, we want this equation to be exact, which led us to this equation, right? And so we're just kind of leading ourselves through the logic. Then this equation led us both to this equation, right, or the last equation. Okay, And so you should be able to reproduce kind of the steps in between, be able to do the logic. Okay, I thought we were going to get away with 3 videos in this one, but it looks like we're going to go to 4. So we're going to do, this is, by the way, this is called exact equation with an integrating factor. And so the mu is called the integrating factor. I think we need an example where we use an integrating factor and we'll work it all the way through. So we're going to have one more video with just an example. See you then.